Welcome Mechanics of Materials students. This lecture is on strain measurements, and for this we're going to be focusing on a particular type of strain measurement called a strain gauge. So strain is measured in a lot of different ways, and what we're typically measuring is actually displacement, and then referencing that displacement to a known length of a material that usually has known temperature and displacement versus strain characteristics. So something that is elastic, linear, that has a known temperature response. So the two main ways that strain is measured today generally is either optical interference for very small strains. Those are usually done in the lab, or more commonly a device known as an electrical resistance strain gauge. And if you want to think about how that works, it's really very, very simple. And I've shown kind of a representative figure of them down here. But if you think about a very, very fine electrical wire that is doubled back and forth on itself, kind of like a heating element. So it's got a really long length. And you can pass a current through it. So you can say V1, V negative, V positive. A current will flow through this. And we know by Ohm's law with electrical systems, for DC systems especially, V equals resistance times the current flow. So if we're applying a known voltage and measuring current, then the current that we would measure is a function of the resistance. And we know that resistance of any kind of conductor is going to be the resistivity of the material, which is a material property, varies with temperature, somewhat with strain, but not so much, and then times the length and divided by the cross-sectional area of the conductor, which is this fine wire over here. So if we fix our small folded bundle of wires to maybe a piece of tape or something with a very low modulus that is going to move with our part, and we adhere that to the side of our part. I'm freehanding this. And then the part moves, the wire is going to stretch, and this length is going to increase, and so the resistance will increase. And so if we use a known current, we can measure a voltage drop. We usually need to use a bridge circuit to detect this. They're very small values, but the good thing is these little folded wire bundles are extremely small, and so we can place them at various different points on a structure or a part, and so we can approximate strain at a point. So we can get the state of strain as a function of location by placing a whole bunch of these all over the place. So it's a very powerful tool to take us from a strain state that is a function of location, which we might want to know for design, from just what we could maybe calculate from loads and average cross sections. So the trick when we get our data from a strain gauge is we're going to get the data that it gives us, and that's going to tell us strain at that point and in the directions that these folded wire bundles are oriented, and nothing else. From that, we might want to know the strain in different directions at that point, because that gives us a lot more information. Like, we may not pick up the max shear or the principal normal strains, which are what we kind of need for design. So this is why this section is, the strain measurement section is in our strain transformations, because what we're going to focus on is the use of strain gauges, because they're workhorse tools for strain measurement. They're cheap, they're easy, and they're very versatile and well understood. But we're going to use what we know about strain transformations to take the data that our strain gauge is giving us and determine maximum shear at that point and our principal normal strains, because that's really the most important thing we need to know from a design standpoint, and at what angle those occur versus the angle of the gauge. The gauge is literally usually adhered with some kind of low modulus adhesive, but strong, to our part. So if we have a part that has a direction that we're designing around, like the axis of a shaft or the top of a beam, the gauge is sitting right on the part. So a relevant reference XYZ coordinate system from the standpoint of the gauge, we know what that is because we stuck the gauge on the part. So orientations relative to that, where we might find our max strains, shear or normal, are what we need to get via a strain transformation. Because our reference system is a system, our reference coordinate system is where the gauge was pointing. It's right there on our part. Okay, so looking at strain gauges, there's two typical configurations you'll find them in, and these clusters of strain gauges oriented in different directions are called rosettes, I guess because they look like a flower. So you can have a rectangular rosette where you have one gauge that's kind of like vertical and two others that are crossing it at 45-degree angles. Or you can have them three equiaxal at 60 degrees apart. And the only thing different is the geometry necessary to accomplish your strain transformation and get the data from it. We're going to focus on the rectangular just because it's a little bit easier to explain and drop into a Mohr circle, but every point that we'll go through in going from the strain measured right off the gauge in whatever direction it's oriented on your part to principal directions, max shear, that would carry over to an equiangular just with different geometric considerations. So let's think ahead towards this 45 degree orientation on our rectangular. It's particularly nice from the standpoint of a Mohr circle because if we look at gauge C and A, they're at 90 degrees apart. So if I were to plot the strains that I've measured on C and A on a Mohr circle, they'd be 180 degrees apart on a Mohr circle by definition. Now they don't necessarily represent principal directions, but they're 180 degrees apart. So I've got the diameter of the Mohr circle. Anytime you have the diameter of the circle, you can get the center. Once you have the circle center, you only need the radius in order to plot the circle, and then you can get principal directions and max shear and shear and normal strains at any other direction. You really only need two. Circles are nice. You only need two pieces of data to plot it, and then you have the whole thing. You can also notice that B, being at 45 degrees to either A or C, is going to be 90 degrees from either A or C on the Mohr circle. And in fact, let me erase a little here. It's going to have a particular clockwise or counterclockwise direction versus A or C. So if we look at B, it's actually 40 degrees counterclockwise from A, because if you go around in this direction, you're going counterclockwise. So that same directional relationship between the strains of those 2 points will carry over into the Mohr circle, except double the angle. So B the point representing the orientation for B will be 90 degrees counterclockwise to whatever we determine it to be for A. Which brings us to the last most important point. These wires we're not measuring shear with them. We can only measure normal strain. So the values that we get plotted, strain values from our resistance changes in our gauges, those represent normal strain only. So we're going to get basically only the horizontal component of the Mohr circle coming from each one. But we know the directions, or we know the angles between them, we know the center of the circle, so all we have to do is a little bit of right angle trig to get those Y components which correspond to shear. So, and it's also obvious why we have to put them at different angles, because that by putting these at multiple different angles, we are able to indirectly capture the shear strain, and the Mohr circle is really the easiest way to represent it. So we're going to go through a few steps that just kind of simplify the geometry, going from gauge data to the Mohr circle and then kind of reinforcing what we know about Mohr circles. We will not have to use the strain transformation data or equations for this. We're simply going to use their Mohr circle equivalent, so we're using them indirectly. So the first thing we'll do is we'll take whatever data we got off of our gauges and we will plot them in the order of magnitude on the horizontal axis. That's the E epsilon axis of the Mohr circle. They're only normal strains. There is no shear associated with those as plotted. So we're going to plot them as they are, right on the horizontal axis. Then we're going to start thinking about angles and remembering that gauges A and C are going to be 180 degrees apart on the Mohr circle because they're 90 degrees apart on the part. And so that will give us our basically 2 points on the Mohr circle, and that'll also give us our center. Then we get to a little bit of decision making. We know the strain for gauge B, and we know that it's rotated 45 degrees counterclockwise if you set your gauge up like this from A. So we're going to plot it 90 degrees counterclockwise from A on the Mohr circle, and at that point the value we got for B will determine where we place the point B, and that's what will effectively end up giving us our radius. And once we've done that, we'll use the geometry of congruent triangles to actually get our radius of the Mohr circle, and then we can determine the strain at any orientation on the part at the point where we put the gauge. Okay, so we'll explain this with an example. So we've got some part sitting out here. It's I've just drawn it, some metal part, and we put the gauge on the surface. So this is the part surface. The gauges are only used on surfaces. We literally stick them to the surface. There are devices that you can place interior. You can drill a little hole and put things sometimes. That's not what we're talking about, and those have different considerations in interpreting the data. So one of the things to remember is we're stuck on the surface. We're definitely going to have plane stress considerations because there's no stress available on one surface, and we're not necessarily measuring strain in the direction normal to the surface. So effectively we can be confident with our plane strain assumption. We don't have to worry about another Mohr circle in a direction where we have to consider that maybe that Z normal coming out of the surface. So that's another nice feature of the strain gauge. It stays in it basically represents a plane strain consideration on your part. So we've got A going in one direction, B is 45 degrees counterclockwise from A, and C is 90 degrees counterclockwise from A. So we get the following microstrain data. We get 100 for A, 200 for B, 900 for C. So we start plotting them on our Mohr circle axis. Here's 900, here's 200, here's 100. So the circle center is going to be at 100 plus 900 minus 100. So that's 100 plus 400. O is at 500 microstrain. So now we have to pick up point B in order to get the radius of the circle. We know B is at 200, and that whatever point is going to correspond to B on the circle radius, this is just epsilon B is just the projection of whatever is going on at point B down onto the horizontal axis, because the strain gauge can only pick up normal strain. There could be some shear, we're just not seeing it. B could be down here, or theoretically it could have been up here. But of these two options, one above the horizontal axis and one below, only one of those two positions will place B at 90 degrees counterclockwise from A. So B is in fact down here. So let me erase here. Knowing that we're down on that counterclockwise path, we can erase here. Now we pull out our congruent triangles relationship, and this is just literally right angle trig. So the triangle that is formed by EA, actual point A on the Mohr circle here, and the triangle formed by epsilon B, B, and O. These two triangles are called congruent because that side of triangle EAO is equal in length to this kind of base of B, EB, and O. So that sets us up to have our y-axis here. We already know our x-axis on triangle EAO. If we have this upright, this shear strain component, we have R by Pythagorean. So the gamma at over 2, as its tensor shear strain, at A here is going to be equal to EB minus O. EB was 200, O was 500. So this side length here is 300. So this side is 300. So we know, now we look back and go, okay, we go from EA to O, which is 400, and we have 300 on the upright. So we can use Pythagorean theorem to get R. So it's a 3, 4, 5 right triangle times 100. So we end up with R equal to 500. So now if we swing R all the way around, it's going to have to go through C and B. I'm drawing a really lopsided circle. So now we have our principal normal strains. So we're gonna stretch the most in this direction. So if we take point C, which was pointing like straight up on our part, if we rotate angle beta counterclockwise from C, so that's 1/2 beta on the part. So if we point in this direction on the part and amount beta over 2, that's going to be the place where the part stretches the most. It elongates. So if we have a bearing or a clearance or something we have to respect and we have some loads applied and we're worried, oh, where's it going to hit the side of a sleeve or a bearing? That's a good place to be looking. If it's going to impinge anywhere, it would impinge there because it's stretching the most in that direction. And likewise, if we had to say, if we had like an O-ring that we had to make sure it was staying compressed, that's absolutely essential for sealing, is to make sure that you have enough squeeze, enough normal strain across the diameter of the O-ring. You'd be concerned with what direction this is, our second principal strain, because that's where you have the least stretch or maybe the most compression. So those are just two examples of where you would care about scenarios that might lead you to needing to know max stress or max reduction in length, and then of course max shear. It's 500 microstrain. So how do you get beta? Well, we already know epsilon, we already know this value, and we know O to EC and we know R, so we can just simply get back beta out with an inverse cosine relationship. So literally 3 numbers, 3 measurements, an appropriate placement of our gauge on the part. You can place that gauge oriented any way you want. So if you already suspect that one direction might be a principal direction, there's no reason to not put one of the gauge directions on it. You notice that EC isn't too far from being the principal direction. So this angle beta isn't very big, actually. So we know max shear, we know the principal strains, and if we said, hey, this is a direction of interest over here somewhere, well, we could just go to our part, we could do some measurements on the part and say, what's that angle? Oh, it's maybe 10 degrees clockwise from A. We can come over here and go, all right, what's 10 degrees clockwise? It's something up here. Oh, the shear strain is going to be greater. And the stretch is also going to be greater. So it's an example of how once you've got your Mohr circle plotted and you can relate directions on the circle to directions on your part, you're home free. You can determine strains in any orientation, but with a caution, it is specific to that location. What's going on over here might be very, very different because we don't necessarily have a uniform stress state along the part, and we are of course also assuming that all of our elastic constants are staying the same from one point in the part to another. So we're assuming homogeneous isotropic behavior without necessarily saying we are. But assuming you were homogeneous and isotropic and your stress state was uniform, then basically one strain gauge would give you a picture of strains in any orientation anywhere in the part. So let's do one more. So we've got our strain gauge. We're going to assume, I'm going to draw a little red line to say this is some crazy shaped part here. And we put our gauge at this point, and so we got our little wire gauges going in. It's these are really small compared to the scale of a part. That's why they can approximate strain at a point. So A is going in this direction. We'll call it horizontal. C is vertical. So A and C are separated by 90 degrees. C counterclockwise to A, just like we had in the other, and B 45 degrees counterclockwise to A. So that'll be 180 and 90 on the Mohr circle. And so we've measured compressive strain at A, no strain at B, and 400, this is microstrain units, of tensile strain at C. So here we go. Put them in order on the Mohr circle. It's like a recipe. Follow the recipe. It makes it easier to make the geometry work. 400, what's the next lowest? 0. So there's B, negative 200. So all we measured were normal strains. We're going to plot normal strains right on that horizontal axis. So now we can get the center of the circle. So we have negative 200 there, 400. Half of that is 300. We add that to the negative 200, and here's our center at positive 100. Now we look at where we're going to put B. B needs to be 90 degrees on the Mohr circle counterclockwise from A. So here's A. I'm going to go counterclockwise. So I'm going to get some point down here somewhere. So here's the normal strain associated with B, which happens to be 0. So B is not up here. We know B has to be down here somewhere. Where down there? Now we use our congruent triangles. So here's triangle 1. And triangle 2 will be down to this somewhere. We don't know that. That's 300 yet. So we know that the base of EA to O is going to be equal to basically the height of our EB to B. So EA to O is 200 plus 100 is 300. So epsilon, or EB down to B, is 300. So here's our point B. So now we can use Pythagorean to get R. So we have 100 microstrain here, 100 squared plus 300 squared, take the square root, and R turns out to be 316. Now we can swing R around, give us our point C, or get through point C. We can give, now that we have R in the center, we can give ourselves every point on the Mohr circle. But more importantly, we can get C, which will help us when we want to look at how far from a known direction our principles are. So if we plot our circle, now we know that this is R, this is 316 microstrain. We know that O to EC is 300, so we can take 300 divided by 316, inverse cosine, get beta. We can also use reverse Pythagorean to get this value, which, by the way, because A and C are on a diameter, we know is the same as this, which is 100. So we know the shear strains at A and C, we didn't measure them from our gauge, but there was shear there, we just couldn't see it. A and C were not principal directions, which we can see that on the Mohr circle, but we were only getting the normal components. So we know that if we swing R around from, R is 316, so we can go from point O at 100. So our maximum stretch in terms of tensile strain is going to be 416 over here, and then from O at 100 minus 316 will be negative 216. So A and C weren't too far off from the principal axes. They were rotated, A and C were rotated just a little bit, basically 9.4 degrees on the part. They were rotated clockwise from the principal. So the principal, let's see, A would be somewhere like that. And C, or sorry, this would be, oh, I'm using stress symbols. I'm trying to plot my normal directions over here on the part, and now I can't erase. I'll just overwrite it. I have a very, very angry computer that doesn't want to do anything. Okay, I'm going to point to it. Oh, there we go. So this line here where you're hopefully seeing a little square, that's the line that would correspond to our principal normal strain that is minimum, so compressive in this case. So it's rotated 9.2 degrees clockwise of A. So on the part, it's up here. So that's where the part's gonna squish in the most, and it's going to elongate the most in this direction. So A and C came pretty close to capturing the principal normal directions. And of course max shear is equal to the radius. So max shear strain is, and that's tensor shear is 316, and so we would multiply that by 2 to get our engineering shear, which corresponds to the change in a 90-degree angle somewhere. So that's 2 examples of using a strain gauge and the Mohr circle version of our strain transformation expressions to go from a really simple measurement at a point to an understanding of the shear and normal strains in any direction relative to that point. And then we can add, in the case of an elastic material, something that's behaving in its elastic range, where we can apply Hooke's law. If we know the principal normal strains and we know the max shear strain, then we can correlate those two to max stresses and to compressive tensile and compressive and shear stresses through Hooke's law. So we can do tau equals shear modulus times gamma, and we can do the full Poisson's and elastic modulus expressions to get stresses and strains in our normal directions. And caution though, if the material is not isotropic, that's not going to hold. You can't use that if the part is not isotropic in the plane that we've measured strain. You can still figure out where the strains are maximum and minimum, but you can't go back through Hooke's law and correlate that to stresses if you don't have an isotropic material in the plane that we've measured, because maybe it was stiffer or a lower modulus in some direction. That could have corresponded to our change in strain even if the stress state, wasn't following. So we're making a couple of big assumptions in this case, and last but not least, we are specific to a point. So we could take this measurement, we could paste 10 strain gauges all over that part and see if the direction of principal strains ends up being the same at every point. If that's the case, and we already know that the material is isotropic and homogeneous, then we could say, hey, we have a pretty uniform stress state. And vice versa. So complex parts won't necessarily have uniform stress states, especially near sharp corners and changes in dimension. So last but not least, you could have used a similar method for equiangular rosettes. The geometry is a little bit more complicated. There's plenty of references to that in most standard textbooks, so we're not going to go over that. It's basically you create another little recipe of how to plot your normals and then construct your radius, but it's just another geometrical relationship. You will still have 2 theta on the Mohr circle corresponding to 1 theta on your part, and preservation of the clockwise counterclockwise relationships between gauge orientation on the part and the circle. So that is it. Please have fun practicing interpreting strain gauge data. You should have some in your homework exercises so you can measure your principal normal strains and max shear strains on a part coming from a given set of gauge data.